Please help me welcome our speaker for the morning, Dr. Katie Bouman, Assistant Professor of Computing and Mathematical Sciences, Electrical Engineering, and Astronomy at Caltech. Dr. Bouman is a Rosenberg Scholar and the recipient of an NSF Career Award. Dr. Bouman's research focuses on computational imaging. She is working to design systems that tightly integrate algorithm with sensor design in a way that makes it possible to observe and measure phenomena that until now have been inaccessible to investigators using traditional methods. At Caltech, Dr. Bouman's research group combines ideas from signal processing, computer vision, machine learning, and physics to find and exploit signals that can accelerate the rate of scientific discovery and broaden the applicability to technical innovation. Katie Bouman received her bachelor's degree in electrical engineering from the University of Michigan at Ann Arbor in 2011. In 2013 and 2017, respectively, she earned an MS degree and her PhD from MIT, both in electrical engineering and computer science. Prior to joining the Caltech faculty, Dr. Bouman was a postdoctoral fellow with the Event Horizon Telescope. Dr. Bouman, welcome to the Greenway Talks online at Palomar Observatory, and thank you for taking the time to speak with us today.
Yeah, no, thank you so much for the very kind introduction. Thanks for inviting me. I'm really enjoying all these puns, so maybe we can, maybe we'll have some more fun with puns at the end. But before I start, I wanted to also quickly apologize to all of you who showed up for what was supposed to be my talk before. There was a mix-up on my part, and I sincerely apologize for that, but I'm so glad that Steve gave me a second chance to come talk to you all. And I'm looking forward to getting a chance to talk with you more and answer questions and have more of a discussion at the end. So today I'm going to talk to you about capturing the first picture of a black hole and also what is to come in here. So black holes, as you know, are one of the most mysterious phenomena in the universe, and scientists have been studying them since they were first predicted from Einstein's theory of general relativity just over 100 years ago. And in particular, for decades, scientists have been studying this giant elliptical galaxy that's at the head of the Virgo constellation called M87. And this galaxy, M87, is 55 million light years away from us and very special. And that's because over 100 years ago, someone actually discovered the streak of light on the sky, which ended up being a galactic scale jet of plasma that was shooting out of the center of the galaxy and marking the spot of a supermassive black hole. And so over decades, scientists tried to develop better and better instruments in order to study this jet and the supermassive black hole predicted to be at the center. And then in April of 2017, we hooked up an Earth-sized telescope and collected the data to make the very first picture of a black hole. And so 2 years after processing the data, this is the image that we saw. So this black hole image was the result of a group of hundreds of scientists and engineers from all around the globe that worked together to build a computational Earth-sized telescope that could take this image. And so today I want to tell you an abridged story of how we were able to take the first picture of a black hole. And there are many, many different angles to this story. This brought together many different people, from theory to instrumentation, to algorithms, to data processing, signal processing. Everything had to come together for this image. But today I'm going to give you a glimpse of my little piece of the story, which was how imaging was done and kind of validated. And then at the end of the talk, I'm going to talk a bit more about techniques that we're currently developing in my group at Caltech to push the Event Horizon Telescope past its current limits to see environments around black holes that are still invisible to us. In particular, I'm going to talk about how we're developing new artificial intelligence machine learning methods to optimize the placements of the next telescopes we build into the Earth-sized array. Okay, so the first question you might ask is, how are we able to take a picture of a black hole that by definition doesn't let light escape, should be unseeable. Well, light propagating near a black hole doesn't follow straight lines. It's curved because the black hole is curving space-time. And so photons can even go in complete circles around it. So the space around a black hole is going to be, it's lit up by this hot gas, heated to hundreds of billions of degrees. And so you have these photons that are flying around everywhere. And some of these photons fall into the black hole, but other ones just graze the boundary and are bent by the black hole's immense gravitational pull, such that the net effect is essentially that the black hole casts a shadow on bright surrounding emission that's almost perfectly circular. And so if Einstein was right about general relativity, this light would be bent into a ring whose size and shape tell us about the mass and the spin of the black hole. And this ring is referred to as the black hole shadow because we're seeing the imprint of the black hole on the backdrop of hot gas. Here is actually a more realistic simulation of what we would expect to see if we had incredibly high resolution and we could see at around a 1 millimeter wavelength. This is what computational theorists have predicted that a black hole would look like for many years. But even then, taking this picture, even though we know that a black hole should make an imprint, taking that picture is incredibly difficult. That's because the size of this ring is incredibly small. It's about 40 micro arc seconds in size, which is about the same size as a grain of sand. But if that grain of sand is in New York and I'm viewing it from Caltech in Pasadena. So, and taking a picture of something that small is incredibly difficult. And it all comes down to the limits of diffraction. And so what diffraction says is it gives us an equation for what are the smallest things that we can see given we have a telescope of a certain size and observing at a particular wavelength. So if we plug the wavelength and required angular resolution necessary to see the black hole shadow into the diffraction limit equation, we can calculate that in order to see the black hole ring, we need to build a telescope 13 million meters across, or essentially the size of the Earth. And if we could build an Earth-sized telescope, we could just start to make out that distinctive ring of light that's indicative of the black hole's event horizon. Okay, well, obviously building a single-dish telescope the size of the entire Earth wasn't possible. But by joining telescopes located around the world, I've been working as part of an international collaboration called the Event Horizon Telescope Collaboration that built a computational telescope the size of the Earth that is capable of resolving structure on the scale of a black hole's event horizon for the first time. Joining telescopes, like distinct telescopes together like this, in this manner is called very long baseline interferometry. So how does this technique work? Well, we have telescopes across the world that are scattered around the world, and they're linked through the precise timing of atomic clocks. So at each telescope, we have teams of researchers that essentially freeze the light by recording petabytes of data that are timestamped by these clocks. And then we bring it all together and use our computers to act like the lens to make the picture. So how do we do that? How do we make the picture from this data collected at these disjoint sites? Well, unlike in a camera, in the Event Horizon Telescope, we don't capture the picture in pixel space, but we instead capture in what it's called its frequency space, which if you don't know what that is, don't worry, it's just a different space that describes the measurements of what the image looks like. So essentially we are capturing measurements of what is called the black hole images, its Fourier transform. And if we put telescopes all across the globe, if we covered the globe in telescopes, we would sample all these spatial frequency measurements, all the measurements we'd need to make that picture. But since we only have telescopes at a very few locations, that means we only get a small number of measurements. So it turns out that for every 2 telescopes we have in our array, we get a single measurement of the underlying images, a 2D spatial frequency that's related to the projected baseline between the telescopes. So for every 2 telescopes in our array, we get 1 measurement. And we need that entire set of measurements to make the picture. If we knew full information. Okay, so just so it comes in handy for later, each of these measurements is a complex measurement, meaning it has an amplitude and a phase, which will be important to remember for later. So in the Event Horizon Telescope in 2017, we only had 8 different telescopes around the world. But actually, of those 8 telescopes, only 5 of them were able to see the black hole in M87 and were at different locations. So that means that we'd only have 5 choose 2, which is 10 measurements to make a picture from, which is an incredibly small number of measurements. But luckily, as the Earth rotates, we obtain other new measurements. So since the baselines between telescopes change as the Earth rotates, this amounts to carving out different elliptical paths in the spatial frequency plane. So we get more measurements in that space of measurements that we need to measure to make that picture. To get these measurements, we record hundreds of terabytes of data at each telescope. So here you see my friend Lindy Blackburn. He's posing with about half a petabyte of data that we collected at just one of the telescopes. And we have so much data that we can't send it over the internet, and so we have to fly it to a common location. And at that common location, we use a special purpose supercomputer called a correlator that combines the precisely timed data. And once this is done, it's passed on to the calibration stage, which finds weak signals hidden in the correlator output by tuning parameters to extract a stronger signal. And so this is an essential step that required many algorithms to be developed before imaging even started. But once we got these measurements, this question still remains of how would we recover an image? So at this point, we have this data, and we can kind of abstract away the astrophysics of the problem and think of it as purely a mathematical problem. We have sparse data we've collected from the pairs of telescopes, and our challenge is to use that sparse data to find the image that caused it. If we were given measurements that covered the entire measurement plane, this would be trivial. In the case of no noise, we would simply need to apply an inverse function called the inverse Fourier transform to them to get back the image. But because we only see a few samples, there are an infinite number of possible images that are perfectly consistent with the data we measure. Because all the regions where we haven't measured data, you can put any number there. And so there's an infinite number of solutions that will describe the data we've seen. And on top of that, the fact that there's a different and quickly changing atmosphere above each telescope across the globe causes our data to be very noisy. And and I like to explain a little bit about how this noise enters the system, because it kind of goes into how we actually do the reconstruction process. So the whole reason that the Event Horizon Telescope works in the first place is due to the fact that light from the black hole is going to travel to Earth for 55 million years, and then it's going to reach one telescope slightly before the other one. And that slight time delay is key for extracting the measurements we use for image reconstruction, those measurements that have an amplitude and phase. But remember, our telescopes are scattered across the globe. So we have a telescope in Hawaii, and one in Spain, and one in Chile, and each one of these has different atmospheres above them. And each atmosphere leads to an additional random a propagation delay, which results in a phase change in our measurement. So now we've had our measurement that should be described by amplitude and phase. Now we're going to scramble that phase. Similarly, the atmosphere also causes a different attenuation factor in the signal, causing a changing absolute gain term. And so this error is very challenging because ideally we would measure this nice, beautiful Fourier component, the measurement that we want to make, the italicized B here on the right. But in reality, the atmosphere causes us to have a completely random phase error in our measurement, and then sometimes a pretty bad amplitude error as well. And so that's pretty terrible because the measurement we end up measuring, the one we get, looks nothing like the one that we ideally would have. We've lost both our amplitude and our phase information. And so in that case, kind of what do you have left to work with? Well, luckily, our measurements, there's extra structure in them. So remember that every measurement we make here is a measurement that is formed by 2 telescopes. But the errors that we have, the errors that enter into the system are happening at every individual telescope separately. And so that means that if we have a 3rd telescope, then the measurements that are formed with that 3rd telescope share some of the same corrupting terms, G2 and Phi2. And so that means that there's redundant corruption that occurs across the measurements we take in our array. And so we can design algorithms that take advantage of this redundant corruption when solving for our images. And so to do that, we developed 2 kinds of classes of imaging algorithms to tackle the problem. The first class of algorithms is based on very standard methods used in the radio interferometry community. The idea is called clean with an iterative self-calibration loop. And this is a traditional method of making images in radio astronomy, which made it a huge plus. And it was really important for us to use it for that reason, because it was vetted in the community understood it. But the real disadvantage of these methods is it was originally developed to work on telescopes that had more telescopes involved or less calibration errors. And so for data like from the Event Horizon Telescope, oftentimes you would need a significant amount of guidance from a knowledgeable user in order to use these kind of approaches. And so because of that, we developed a second class of approaches, which we called regularized maximum likelihood ones. And in this method, we don't try to find an inverse function that takes us directly from the measurements to a picture, but instead we try to find a picture that when we pass it through the telescope system, a mathematical model of the telescope system, it produces data that is similar to the data that we actually see and is also a likely image that we define through some sort of what is called a regularizer or prior, which I'll explain in a little bit. So the disadvantage to these methods is that we had to define what is a likely image. And that is always going to introduce some sort of bias into what kinds of images we end up selecting in the end. But the huge advantage of these methods is that we could naturally incorporate all the different kinds of errors that we expect to see in the telescopes, like the atmospheric error I just talked about. And so we can result in better images in the case of challenging errors that we see. So just to briefly summarize this kind of regularized maximum likelihood approach, we modeled the forward telescope system as a function f of x here that returns data we would likely see y hat if the true image in the sky were actually x. But since we don't observe all possible measurements, since we only have sparse data, that means that there still will be an infinite number of images that give us the exact same y hats, because y hat is only measured at a small number of points. And so that makes the problem ill-posed. There are many images that are equally likely. However, although there are an infinite number of images that are equally likely in terms of the measurement likelihood, of the images that are consistent with the measured data, there are some images that are more likely than others. For instance, perhaps we think that the image on the left is too messy, and we prefer images that are sparse and compact. And so we can mathematically define these kind of preferences, and therefore our goal then becomes to find an image that doesn't just fit the data, but is likely under some sort of mathematical model of good or likely images. And so using this idea, we incorporate what we call an image prior that essentially scores the images. And so we solve then for an image that both maximizes the data likelihood, so it fits the data we've seen, and is also likely under our mathematical model of likely images. And using this idea, we can whittle down from the infinite possibilities to a single image that we think is a likely image that fits the data well, even in the presence of all that kind of crazy noise I talked about. All right. So that's great. We can come up with these methods that allow us to recover images from the sparse data from telescopes distributed around the world. But note that even if we can develop methods such as these to recover a single image, we always have to be really cautious. And that's because any imaging method we come up with, whether it's the more traditional clean method or this regularized maximum likely approach like I'm showing here, or anything else, if you do a fancy machine learning approach, whatever you try to do, it's always going to require that we inject some additional information into the problem about what images look like to recover something back in the end. You can't get away from that fact, from having to do that. And so that meant a big question we've dealt with in M87 is how do we verify that what we're reconstructing with our imaging algorithms is actually real? We didn't want to accidentally have a preference for, even subconsciously, for something like ring images and then be super excited we got a ring back in the end. And so we had to spend a lot of time thinking about this problem of how do we verify our images? And we tackled this through a multi-step process. The first step actually began years before we even collected data of the black hole, and that was to run synthetic data tests. So we did this through what we call the Event Horizon Telescope Imaging Challenges, where we'd have a team of people simulate realistic data sets, so they'd choose an image and they say, I want to generate synthetic data as if the telescope were seeing this picture in the sky. And then they would distribute these data sets without giving any hints to what the true image was. And then from just that data, that synthetic telescope data, we'd have teams of people that would use their favorite methods to reconstruct the images and making their best guess at what the image is. Then using these images, we passed it off to a team of experts who would look at them and try to decide, what do I think the underlying structure actually looks like for these pictures? And this was actually what we would have to eventually do for the real Event Horizon Telescope data, because we don't know what the true source looks like. And so just using our reconstructions, we'd have to try to make a guess at what was there. However, unlike in the real data case, because the data is simulated, we could eventually evaluate how close those reconstructions were to the true image. And so I want to show you a few examples of things we saw in these imaging challenges to try to show you how we use this information we learned there, the lessons we learned there, to actually approach the real black hole M87 data. So here's one example from a challenge. On the top is the true image, although that was hidden from the people while they were making the reconstructions. And on the bottom were 5 submitted images from using different methods. And so each of these images was reconstructed independently in one another. And although that is the case, they all still have pretty consistent structure. There's, it's kind of this ring shape where it's brighter on the left side, left side than the right side. And so although they all have a very consistent structure, there are differences among them. So some of them have wispy structures in different places. And so by looking at what is consistent and inconsistent among the images that are obtained using different kinds of methods, we can try to build confidence in certain features and reject others as possibly just an imaging artifact that we've accidentally hallucinated. But we also wanted to check ourselves and make sure we could see something totally surprising. So we'd also sometimes throw in random things into the mix. Here was one of the challenges that I really like, where I threw in a snowman. And obviously, no one was expecting a snowman to be at the center of the galaxy. And obviously, the imaging methods weren't expecting anything like this either. But despite the fact that, this was some very weird structure, all the methods were still able to get something that somewhat resembled the snowman. Although it's quite funny of what people's interpretations of what they were seeing, where a lot of people thought it was a binary black hole system that they were looking at. But doing a test like this gave us confidence that we would actually be able to see something surprising with our real data. So based upon the synthetic data test, we developed how we were going to actually approach the actual M87 data. And so like in the imaging challenges, we wanted to avoid shared human bias so that we could assess common features among independent reconstructions and try to see, are these features consistent across different, using different methods, or are they different? And that would help us build our confidence or reject other features. And so to do that, we split about 40 people who worked on the imaging into 4 teams that span the Earth. And these 4 teams were not able to talk to each other actually at all during the imaging process. So when we got the data, we actually split ourselves into these teams, and we worked in isolation for 7 weeks trying to make our best image from the data. And then after 7 weeks, we all gathered together in Cambridge, Massachusetts, and we revealed the images to each other. And this is what we saw. So this was quite amazing. Although each picture was different, each image came from a different team, so different methods were used to generate that image, each of those images. Despite that, they all kind of reconstructed the same basic structure, a ring of roughly 40 microarcseconds that was brighter on the bottom than the top. And so seeing these images was incredibly exciting, because it brought a whole other level of confidence to our results, as we found that no matter kind of the method or the person that was reconstructing the data, we always saw this ring pop out from it. And so without having done a test like this and having different people reconstruct with different methods, I don't think we would have ever achieved the same level of confidence we have in our results. But we still wanted to make sure that we weren't imposing some sort of human bias. Just because We had avoided shared human bias by splitting ourselves in teams and independently reconstructing. That didn't mean that we weren't imposing human bias at all. Maybe maybe when I'm making an image, I want to see that ring pop out. And so we basically tried to spend the next couple months after we got this picture trying to break our images and make sure that it actually was a ring. And so that led to the next step, where we tried to objectively choose image parameters to remove humans from the loop as much as possible. And to do that, we developed 3 different imaging pipelines. So 3 different kind of code bases that we used to reconstruct the images. Each of these, and you can actually download these code bases along with the data online, so you can run them and modify them however you'd like. But each of these pipelines was developed with different knobs on them that are, and those knobs specify different hyperparameters that are used to slightly change the results of the reconstruction. So these hyperparameters are usually tuned by a human user who has intuition on what kind of hyperparameter settings will get a good image. But instead of having a human tune them, where we might be injecting some of that human bias, we instead wanted to search for the best set of knob settings to recover different kinds of source structures and then see how those settings affected the M87 reconstructions that we get out of the black hole. So for instance, we generated synthetic data as if the Event Horizon Telescope were actually seeing a disk on the sky with no hole in the center, and we found the best set of parameters, beta, to recover this disk shape. And then when we transferred these exact parameters onto the M87 data, we found that although we had tried our hardest to find parameters that would recover a disk with no hole in the center, the data required us to put the hole there. And by doing this simple training and testing procedure on many different kinds of underlying sources that we thought could trip us up, we saw that our methods always preferred the ring shape. And that was true no matter the day we observed M87 on, or the imaging code we used to reconstruct it. And so by blurring the images from different imaging pipelines to an equivalent resolution, we then averaged them to form the image that we showed to the rest of the world 2 years ago, this ring of light surrounding the black hole, roughly 40 microarc seconds in size, and brighter on the bottom than the top. So this really, we had many different images that we reconstructed, but this image really embodied what was consistent among all those reconstructions. Once we had made these images, though, we still wanted to make sure they were right. We still weren't convinced they were right. It was right. And so we went through a series of validation tests. We did a number of these. I'm just going to briefly talk about one of them that we did, but yeah, you can look obviously in papers and stuff to see the other tests we did. So previously I talked about how we selected one set of parameters, beta, that performed best on synthetic data, and then we used that beta to transfer onto the M87. But why should there only be one parameter set that we consider? In fact, by doing large surveys over the parameter settings and over different synthetic data, we found that there are often many parameters that actually perform reasonably well. And so what we did is instead we set some threshold and we found all the betas that performed above that threshold and then used those to reconstruct images of M87. And so, for example, for one of the pipelines, we ran hundreds of thousands of different simulations and found that we had about 1,500 parameters that we thought were acceptable. And once we had this set of images, about like those 1,500 images of M87 that were reconstructed with different parameter settings, we could then look across those images for variations. So, for instance, here on the left, we have the mean of 1,500 images that were reconstructed under different parameter settings. And in the center, we have the standard deviation of those images. So you can see that the standard deviation, there's actually 3 bright kind of spots along the bottom. Those are areas that we have more uncertainty in. So across the images, the pixel values there had more uncertainty. But if you look at the standard deviation relative to the mean, you can see that it's actually only a small fraction of that mean. And so if you look at the fractional standard deviation of the images, you can see that actually basically all of our images, most of our images had that ring shape. But what did change a lot across the images was all this wispy structure on the outside. So you shouldn't believe all that stuff, the exact structure of that wispy structure. So that's great. So from lots of different angles, we kind of we got this image of the ring. But the question you might have still is, what did we learn from it? So for instance, one question I get a lot is, did we prove Einstein was right? And well, the short answer I like to say is no, but we also didn't prove he was wrong, which is also a big deal. We kind of proved it, we're consistent with general relativity from a different level. So I want to kind of give you an idea of how we're able to use this picture to tell us about black holes and gravity. So if you take a fixed size mass, we can calculate the radius that we need to compress that mass down to in order to get a black hole. So for a Schwarzschild black hole, that would be its event horizon. But actually, what we generally expect to see is not the event horizon itself, but actually the point at which photons are orbiting around the black hole. So this is called the photon orbit. However, not even that is what we expect to see. So due to the immense gravity around the black hole, this photon orbit, so you have photons going on orbit, but it's an unstable orbit, and so they shoot off towards us. And as they shoot off towards us, the gravitational lensing caused by the black hole causes that ring to become bigger. And so for a non-spinning black hole, the diameter is about 5.2 times the Schwarzschild radius, so 5.2 times the event horizon size in this case. But when you have a black hole that is spinning, it appears a bit smaller. So this range of diameters between 4.8 and 5.2 times the Schwarzschild radius is the range that we'd expect to see, the size of a ring we'd expect to see if a black hole is obeying canonical general relativity. And notice that this directly depends on the mass of the black hole. So for a smaller mass black hole, this ring actually becomes smaller. And that's interesting because actually from past measurements of M87, it was very unclear what the mass of the black hole in M87 was. So gas dynamics pointed us more to about 3.5 billion solar masses, but stellar dynamics pointed more towards about 6.5 billion solar masses. And the stellar dynamics really provided an upper limit, as there couldn't be more mass within the black hole than we saw within the stellar orbit. And so we wouldn't expect any ring bigger than the yellow one. But then we could ask ourselves, okay, how do we turn our image into a test of black holes? Well, we can also look at other unusual and exotic objects. For instance, wormholes also produce a shadow feature, but wormholes have a smaller shadow than black holes. And so here is what one type of wormhole, what it would be for about a 6.5 billion solar mass wormhole, the blue dotted line here. And naked singularities or super spinning black holes also produce shadows, but they'd be even smaller. And so it turns out that when you lay the Event Horizon Telescope image on top of all of these, you find out that all these other exotic possibilities are instantly ruled out, and you're left with a ring that matches nearly perfectly with the stellar dynamical measurement of the black hole mass for canonical general relativity, a mass of about 6.5 billion solar masses. It's an enormous, massive black hole. And so this is just kind of one of the many things we can learn about black holes and gravity by studying this image. We're also learning other things from the image and squeezing more out of the data. In fact, just a couple months ago, the collaboration released new results that don't just show the total brightness of the light around the black hole, but also the polarization of the light, the direction of the light. And polarization reveals information about the black hole's magnetic fields, which govern the flow of plasma and launch these galactic scale jets that we talked about at the very beginning. And so by analyzing the data in different ways, we're already learning, so much about black holes, but perhaps the most amazing thing we see is, or at least in my opinion, is that by comparing this picture to simulations scientists have made for years, we find that the image we've taken was amazingly consistent with a number of these predictions. You know, and at the end of the day, the big thing is that we recovered a ring, which now it might seem so obvious to you that we would get a ring, but that was the big question when we started. Would we see a ring? But you might notice that the video I just showed, the simulation is actually moving. So you might wonder, is the recovered image of M87 also moving? And in fact, it turns out that it is. So another interesting thing is that we actually captured data from the M87 black hole over the course of an entire week. We capture data from 2 days at the beginning of the week and 2 days at the end of the week. And so we could take that data and we could independently recover an image from each of those data sets and string those images together to form a very short movie. And if you do that, you actually might notice there's some variation, some evolution around the black hole. So I'll play it for you here. It's very hard to see, so I'm gonna show you again. You'll notice that the bright spot moves more from the left-hand side, more to the bottom. So I'll play it again. So we don't have a good idea of exactly what's causing the variation. I mean, we know that it should be varying, but we don't know if this is due to rotation of material, just material lighting up or getting dimmer. But what we are sure of is that that time variability definitely exists. And that's because it appears in the raw measurements we take. If you look at the measurements we have over the course of a week, we can see that actually there's a significant difference in the measurements we've made at this, that should be measuring exactly the same thing. And that indicates that there should be evolution. And actually getting a hold on a black hole's time variability is quite important for a number of reasons. It not only gives us a window into the dynamics around a black hole and hopefully an understanding how these powerful jets are forming and things like this, but it also helps us in mapping the space-time of a black hole and constraining our prediction of general relativity even further. But actually the black hole in M87 is not the only black hole we're interested in imaging. In the heart of our own Milky Way galaxy, 26,000 light years away from us, there's a cluster of stars. And by peering past all the galactic dust with infrared telescopes, astronomers have mapped the past of this cluster of stars over decades. And by tracking the motions of the stars over time, astronomers have concluded that the only thing small and dense enough to cause this motion is a supermassive black hole. In fact, this discovery led to the Nobel Prize in Physics, given just months ago for the work of André Ghez and Reinhard Genzel, for the discovery of a supermassive compact object at the center of our galaxy. This compact object, otherwise known as Sagittarius A Star. So as awesome as M87 has been, it turns out Sagittarius A Star, or Sag A Star for short, that resides in the center of our own Milky Way, might be able to help us better answer some of the remaining questions we have. But however, Sag A Star is teeny tiny compared to M87. It's only a measly 4 million solar masses compared to M87's 6.5 billion solar masses. And because it's a lot closer to us though, it should appear about the same size on the sky. But because it is physically a lot smaller, that means gas orbits around it much more quickly. So whereas it takes about 4 to 30 days for gas to make a complete orbit around M87, for Sag A Star, gas makes a full orbit every 4 to 30 minutes. Very fast. And so we'd love to be able to reconstruct not just a static image from the data, but actually full movies of the black hole evolving. But if you thought recovering a static image was a hard ill-posed problem, this ends up being orders of magnitude more challenging. So as important as it is to continue pushing on the algorithmic approaches to squeeze more out of the data, it's also important to realize that in order to extract more science, we also have to think about improving not just the algorithms that we're using to analyze the data, but also our instrument that collects the data to begin with. And so that leads to the last part of the talk today, where I'll be talking a little bit about some work that's currently going on in my group to optimize the next generation of the telescope array so that we can see even more than we can right now. So in 2017, we observed with telescopes, as I said, at 6 different locations around the globe. And making images was really challenging with that small number of noisy measurements. Although in the end we were confident of the ring shape, it took us over a year to build that confidence. And so we've been building out our array to get more data, adding telescopes in Greenland, France, Arizona, and the one I'm most excited about is that we recently got funding to add a telescope at Caltech's own Owens Valley Radio Observatory. So I'm really excited that Caltech, my new home is becoming part of the EHT telescope as well. But imagine what we could do if we added 10 more. Well, maybe we could actually make a video of the gas falling into the black hole at the center of our galaxy. Being able to do this is a huge scientific gold mine. But before we just plop down a bunch of telescopes, we need to be very careful. And that's because building a new telescope is expensive. It costs at least millions, but usually tens of millions of dollars. And so we really should be trying to optimize to find the locations that give us the biggest bang for our buck. So how should we go about solving for the location of telescopes in the next generation array? Well, typically when you're designing telescope arrays like this, the design of the sensors are idealized. The design of the telescopes and where they are idealized and kind of considered independently from the image reconstruction problem. And in doing so, many assumptions are made. For instance, ignoring nonlinearities in the system or complexities in the noise. But for problems where the data is so correlated and the noise is so challenging, like in the case of the Event Horizon Telescope data, it's a huge missed opportunity to not consider them together. And so really we should be trying to optimize both parts of this full imaging pipeline together. And so how should we go about doing this? Well, if you rearrange the blocks in this diagram, you'll notice that it looks similar to something in the machine learning community called an autoencoder. In the autoencoder, which I'll explain in a second, the sensing system is the encoder, which produces measurements or codes, Y here, and then the imaging algorithm is the decoder that takes the measurements and recovers back an image. And so deep autoencoders in the machine learning community, where the encoder and the decoder are neural networks, are often used for image compression. So basically, you solve these neural networks, these AI systems, right? And you solve for weights of these networks, then encode a picture in a small number of measurements at the same time as another network that decodes those measurements into an image. And so we use just kind of like standard machine learning machinery, basically to figure out how to best compress the images into a small number of measurements. In the reconstruction problem, you could use an arbitrary mathematical function that takes you from a measurement to an image for reconstruction. So all we need to do is we have to have something that takes in measurements and outputs a picture of the reconstruction. And so this part can be represented as a neural network. We can train a neural network that takes in measurements and outputs a picture. That's something we can do in a computer. However, unlike in generic autoencoders, you cannot build any kind of mathematical function on the ground, right? We can't just learn some mathematical function in our computers and then go out and build it. We have to make sure we're learning something that we can actually build. And so this is something that we've been working on in my group in order to learning how to design a way to learn the locations where to build telescopes in order to help design the next generation array. And so this has been led by a postdoc in my group, Hassan. And the idea is to develop a physics-constrained encoder that we can train with the decoder, with the reconstruction method together. And so we can learn the best telescope array simultaneously with how to best make an image from those measurements. So the idea is we take an input image Z here, and we can define a forward model of the measurements that we expect to see. So the forward model is like a simulation of our telescopes. And so we have here on all the possible samples all the possible measurements we might make. So in this example, we are pretending we have 3 different possible telescopes to sample that are color-coded blue, red, and green. And we indicate the measurements that come from pairs of those telescopes by these colored dots. And so this forward model, we take an image in and it outputs all the possible measurements we could make with those 3 telescopes. And so here we're showing all those samples, and we could pass all those samples off as our collected measurements to the image reconstruction decoder. But in that case, we would actually have to build all those telescopes to make all those measurements. And our goal is to not do that, not to build all the possible telescopes, but choose among them to find which ones are the best to build. And so to do that, we introduce what is called a sensor sampling distribution that characterizes the probability that we sample from a particular telescope. So we sample telescopes from this distribution, and we mask out any measurements that were not produced by those telescopes. So for instance, in this case, now only the red and blue dots remain because we only sampled the blue and red telescope here. And every time we sample from this probability distribution, we sample different combinations of telescopes and observe different observed measurements. So now these are the observed measurements that we pass on to the image reconstruction decoder. So basically the goal of the encoder network here is to learn which are the best telescopes to sample, and then that selects which of the measurements Y that then get passed on for image reconstruction. And so our goal is to, from a big set of possible telescopes, select which ones are the best. And so we basically string all the pieces of this problem together into a single network, and with the trainable blocks highlighted here in red. And so our ultimate goal is to use this network to learn a probability distribution over where to build telescopes. And we learn this simultaneously with the decoder, that image reconstruction network. So they're really working hand in hand. And we do this by defining a loss that, one, maximizes the similarity between the input and output images, two, encourages sensor sparsity to help reduce the number of telescopes that we build, and three, encourages sampling diversity to make sure we have fully explored the space of possible designs. And so then we learn the sensor sampling distribution with the decoder during end-to-end training. And so basically we solve for the parameters of the system that tell us that are parameterized by two numbers. One number tells us basically how important is it to sample each particular telescope, and then another number that tells us about how, if you sample one telescope, should I sample another telescope or not? So the correlation between telescopes. Why would you ever want to turn one telescope off? Well, to save resources, because we want to find the smallest set of telescopes that performs well. And so we learn the parameters of this distribution then through the machine learning training. So here's an example of a telescope distribution that we've learned. The parameters here, theta jj on the left, quantify the activity or the importance of any one single telescope in our array. And then the parameters theta jk on the right quantify the correlation between pairs of telescopes, where red represents positive correlations and blue represents negative correlations. And from these recovered distributions, we can see some patterns that we would expect to see. So for instance, in the case of simple uncorrelated noise, in many cases, when you have two telescopes at the exact location, they're actually penalized from being sampled together. And that makes sense because in this case, remember that every measurement we make is coming from pairs of telescopes related to the projected baseline between them. So if you have two telescopes at the same location, they'll be just making the exact same measurement. And so you don't want to sample both of them. You want to use that resource to do something else. But what my favorite thing is not things that we would expect to see, but things that we don't know what to expect. So for instance, by changing the type of noise that we expect to have on our measurements, we can use the artificial intelligence and the machine learning networks to learn about what is still the optimal design in this case. And so for instance, here is a result when we had purely Gaussian noise included on the measurements, when we had just simple noise, the simplest noise you can think of. But when we include all that different atmospheric air that plagues our measurements and scrambles our data that I talked about at the beginning, the array preferences actually change fairly drastically. So you can notice that when I flip back and forth, the correlations have changed. And so this finds that it tells us about what structures in the geometry are preferred in the case of kind of the challenging atmospheric air that I talked about earlier. And so these methods that we're developing are giving us a way to not just analyze the data that we're getting out of the telescopes, but using it to actually design the future of our telescope array. And so using this approach, we're starting to understand where we may be wanting to place our next ground-based telescopes to reveal more of the unseen. And I'm also excited that we're also working with JPL to even think about the optimal placement of telescopes in space that we could possibly do in the future, although it'd be an expensive addition to help improve the measurements we make for the telescopes. So to close, it's clear we've learned a lot from this image of the black hole in M87 already, but what I hope I got across in the talk today is that we're really just at the beginning. And now that we have this extreme laboratory of gravity, we're thinking about all the ways that we can go back and improve our instrument, improve our algorithms, improve them jointly with ideas from machine learning to squeeze more out of our data. And hopefully just show you one day a static image of a black hole, but actually a movie of a black hole as the gas is slowly falling towards its event horizon. So with that, I want to thank the amazing team of collaborators that I have the opportunity to work with on a daily basis. There's far too many to name, but I want to highlight Ha, who led the work on the machine learning for the design of the future array that I spoke about. And I also want to highlight all the early career collaborators who really have done all the hard work to make this project a success. And just before I end, I also want to have one shameless plug that if you're interested in learning more about the project, I want to let you know that there's a documentary on Netflix that was just released this week that was directed by my friend and colleague, Peter Gallison. And so it's a really excellent documentary that kind of shows the process of doing science for two interleaving projects. And Peter has done an amazing job with it. So yeah, thank you. And I'm happy to take any questions that you have.
Dr. Bouman, thank you very much. That was a great presentation.
Oh, thank you.
And questions, everybody?
I have a question.
Yeah. Hi.
So thank you so much for sharing all that with us. That was great. My daughter and I watched the documentary as well. Fantastic. But is there a way to take everything that you've learned and all the processes that you've developed here and apply it to gravitational wave observations that are being used, that we're collecting from like LIGO?
Yeah, great question. So LIGO is only sensitive right now to, we're kind of on different wavelengths, I guess. So LIGO is sensitive to stellar mass black holes, so small black holes that are on the order of tens of solar masses. And we're only sensitive to supermassive black holes that are millions to billions of solar masses. So right now, although the project, they kind of provide complementary information, I would say, although there are talks of how can we kind of use, like, you know, think about in the future of maybe observing similar, so, okay, with LIGO, there's an extension that is being developed called LISA that would then be sensitive to supermassive black holes. So although we, you know, then there might be a possibility, although right now the only black holes that the Event Horizon Telescope is actually sensitive to is the black hole in M87 and the one in the Sagittarius A Star black hole. Those are the only two that we know of that are large enough on the sky that we would be able to actually see the event horizons for them. That doesn't mean that we can't see the surroundings of other black holes. So we look at other active galactic nuclei that are caused with other black holes in other galaxies where we can't see their event horizons, but we can see the jets coming off of them, and we study that as well. So that is something that is definitely, there's a lot of conversations, especially with LISA. Would there be a chance for joint observations, or, you know, one that, like, you know, if one is detected, maybe you use that to observe after the fact, after Lisa has identified something. So there's a lot of interest in that. Right now, I think that's pretty far away. There's also interest in connecting to other kinds of observatories, though. For instance, the Gravity Observatory, which Reinhard Genzel is part of, who won the Nobel Prize last year in physics. They have been able to map kind of like these flaring structures around Sagittarius A Star. And so one interesting thing there is if we could jointly observe with them and kind of have different kind of modalities that we're using to try to interpret the variations around the black hole. So yeah, I think there's a lot of interest, and we're just trying to figure out how these pieces might fit together in the future. Good question.
So I have a question.
Yeah.
Do your polar, as I understand it, the two key parameters of a black hole are its mass and its spin. Do the polarization measurements tell you what the spin is?
So I think, so the polarization, so basically we put together, I don't know if I have these, this library. Okay, I must have deleted the slide, but I can show you. Okay, so basically we form these huge libraries of simulations that are done with different parameters, including the spin. And by looking at the initial image that we had recovered, we could try to say what was the most likely set of parameters for the black hole. And actually using by plugging in polarization, we were able to whittle it down a lot more, the set space. So I think it doesn't exactly tell us what the spin is for sure, but it does help us in narrowing the space of possibilities more. It more though tells us about the magnetic fields around the black hole. So I have a video that I didn't have time to show that I can show it here. That kind of shows what the polarization is doing. So you have this hot plasma that is spinning around the black hole, and so you have these threaded magnetic fields. And when your magnetic field strength is very strong, oh, okay, I'll first do when it's weak. When your magnetic field is very weak, then it gets kind of pulled with the plasma that's spinning around the black hole. And the light that then comes off of the it ends up being perpendicular to the direction of the magnetic fields. And so that means that the light is being polarized. It's polarized perpendicular to the magnetic fields. And so your polarization direction, it comes out, you would get this radial pattern that comes out of the black hole if you had a weak magnetic field around the black hole. On the other hand, if you had a very, very strong magnetic field, it can resist the plasma, and it causes you to have, so it like straightens out like these spokes on a wheel. And then still the light is going to come off perpendicular with polarization perpendicular to that. And so when it comes off, you're going to get something that's like the polarization is in a spiral, like going in the direction of the circle, like this. But when you have something that is like an intermediate strength magnetic field around the black hole, you get these like twisty patterns. And so then the resulting polarization field also looks twisty. And so that is kind of more like what we actually are seeing in the black hole that we actually reconstructed. So here you'll see the picture after this of the actual M87's black hole polarization. You can see it has more of this twisty pattern to it. And here's kind of the other picture they show where these lines are showing the direction of the polarization. And so that twistiness is telling us that it's most likely the fact that we have a intermediate strength magnetic field, and that helps to tell us about how like the jets are launching and things like about that. So although it does tell you, it does help us narrow down things about spin, it's not directly as related to the spin of the black hole. So one thing that we're using, that we would like to use to extract more information about the spin is actually look at the temporal evolution. So if you actually look at these bright spots as they're rotating around the black hole, then you can try to map out the space-time and use that to extract information about the spin. And so actually getting a handle on the dynamics will help us, I think, in better estimating the spin of the black holes.
And I was going to ask you that very question. With the technology you have today, how long does it take to collect data on for a given observation? I hate to call it an image. And then how long does it take to process it?
Yeah, so so really good question. So as I said at the beginning, we need to collect data over, let me see it. So we need to in order to get enough measurements to make a reconstruction of an image, we have to look at the black hole over the course of a night while the Earth is rotating. So as the Earth rotates, we carve out these different measurements, and those measurements, we all have to throw them into a big bucket and use that to reconstruct a single image. So the data that we use to make a single M87 black hole image came from a night of observation. But the challenge is, so that came from a night of observation, but actually then making that picture, once we collected the data, then it takes a huge amount of time to actually process that data down. So hopefully that time is becoming shorter as the tools, I mean, this was the first time that we ever had used this new type of telescope right before. And so we had to develop all these tools to get it to work. And so hopefully over time it becomes more streamlined, but nonetheless, even once we collect those measurements, we even have to send it back to a common location. We collect the measurements at the South Pole. That means we even have to wait for their winter to be over. So it takes even 6 months just to ship the data back. And then we have to process it and do all the data analysis. So the first image that we took from the time that we collected the measurements to when we made a picture, it took about 2 years to get to that point. But as we get, hopefully, as the tools become better developed, it becomes much faster. Although, with anytime we're working with telescopes that are distributed around the world, it's never going to be immediate. You always have to bring these things together, and that takes months and of time to process it, to get the data and then to process it and then publish it. But ideally, you're going to get all your data to make one image comes from a course of a night. However, for the M87 black hole, it's kind of static over the course of a night. Because it's such an enormous black hole, that means the gas isn't moving around it very quickly. And so that means all these measurements kind of are like from the same static image of the black hole in the sky.
Mhm.
But for the black hole in the center of our own Milky Way galaxy, it's evolving on the timescale of minutes. And that means that every measurement we make is coming from like a different snapshot of the black hole. And so we have to develop algorithms that then take into account the fact that over the course of the night, it's changing, basically. So there's different, depending on the timescales of the black holes, we have to think about them in different ways. That answer your question?
Yes, it did. So there are whole new frontiers in machine learning and computational science here.
Yeah, totally. I mean, and it's really pushing the boundaries because, it's things like, making an image of a black hole is actually very kind of similar conceptually to taking a picture of like when you go in and get a brain scan in an MRI machine or something. It's very conceptually similar. And that in the MRI machine, you also are taking sparse measurements from the frequency domain, the same kind of thing here, except those measurements are a lot less noisy and a lot less sparse. And so, it's fun to kind of think about how the ideas that we develop for black hole imaging actually, relate to medical imaging and a lot of other kinds of fields, but we have to tailor them for the specific challenges we have in the particular telescope we're working with.
So
Thank you. You're a wonderful explainer.
Thank you.
So I have to pick up on that thread. I have a technical question.
Yeah.
Trying to get a sense of the efficiency of the data collection and processing process. So maybe a way to frame the question is, you collected a bunch of data. What fraction of that data was eventually incorporated into, say, the first release image of M87?
Okay, so we took about in 2017 when we observed, we took about 5 petabytes of data that were collected. That 5 petabytes was not just for the M87 image; it was for other sources too. We also took data from Sagittarius A Star black hole and other AGN as well. But I would say about 1 to 2 petabytes was for M87. And then all of that information eventually is going into the black hole image, but it gets reduced down a lot because we have this tiny little signal riding on a huge amount of noise. And so all this processing, so we have 1 to 2 petabytes initially for M87, it gets reduced down every step of the process, basically averaging out all that noise and trying to refine out that little amount of signal in there. And so in the end, it was only megabytes, basically. So you can email the files around and do the processing on your own laptop computer to make the image. So, all of the data is in there. All that data was necessary, but it gets like only a tiny little bit kind of gets squeezed out of it in the end. So it goes from petabytes to megabytes to kilobytes for the image.
Okay, thank you.
I wonder if it makes any sense to think of when you're unknown phase delays in front of the telescope, if you were simultaneously observing with an adaptive optics system that gives you phase delay information, probably at the wrong wavelength, but is there a way to correlate maybe short wavelength phase delays with longer wavelength phase delays and allow you to at least constrain the unknown phase delay.
Yeah,
That
it's a
makes
really
sense?
good question. So this is, something that we've tried to think a lot about because of the fact that really those phase delays are the most challenging part. If we didn't have that, we could make much better images if we had the known phase information. The problem is that normal adaptive optic systems, and I know you said like, oh, okay, transfer from different wavelengths, but I'll just mention first that I think for adaptive optic systems, they have this beacon, not beacon, a guide star
Artificial
that
star.
they're reflecting off, and that isn't going to work for the wavelengths that we're working with, so you can't do that. I think like some people, you can potentially use radiometers, but I think that I don't know all the details, but whenever I talk to people about potentially using radiometers, it seems like there's too many challenges and it wouldn't actually give us exactly the phase information on the timescales that we need it. And I don't know about how, like, if you can transfer, it feels like if you know the phase at yeah, I feel like you can transfer it, but I don't know how big of a gap in wavelengths you can transfer over. So at least whenever, I'm not an expert on any of this kind of stuff, but when I've talked to people about it, they don't seem to think that that's a possibility. One thing that we have talked about is putting a drone up, very, very high altitude drones, and flying them. But you'd have to have but remember, we have to have the drone in the line of sight of what we're looking at. And so it'd have to be a drone that moves very, very fast and stable at those high altitudes. And when I've talked with people in the robotics groups here at Caltech, they think that because the high winds at those high altitudes, it would be very, very difficult to do that. So, but I don't think it's not a possibility. It's just there would have to be a lot of of new designs and new technology to make that a possibility as well. If we had like
at that point, you might as well put something in space.
Sorry?
I'm sorry. At that point, you might as well put a satellite in space that's emitting a stable radio signal.
But it has to remember track and be in the line of sight of the thing you're looking at. So the problem is the atmosphere, these millimeter wavelengths that we're looking at, it's changing. You can't like it changes very quickly in time, and it changes very quickly in space. And so you have to be right. The beacon would basically have to be right in the line of sight of the thing you're observing at. And so having a beacon in space would be, I think, also challenging. You have to have something that's maneuvering around very quickly. But I don't know. I think the drone thing is a possibility. I haven't given up on that yet. But yeah, another option is you go to space. But that's very, very expensive. And there's other challenges that come in there. Yeah. But I mean, I really like these ideas that you're throwing around. I think we do need to explore them more as well.
Picking up on the idea of putting stuff up in space, the baseline of the Earth is about 13,000 kilometers, the baseline of your telescope. If you could make some sort of an array comparable, the LISA array, or the proposed LISA array, I guess it is optimized for gravitational waves. Could you put up something in space, in principle, that had a tremendous baseline, much, much bigger than the diameter of the Earth? Would that be possible?
Yeah, yeah, it's possible. I think the question is it worth it? So right now, we've actually been having, so I don't know if you guys are familiar with the KISS Center at Caltech, but there's the Keck Institute for Space Studies, and where we've gotten together with people from around the world and from JPL, and we've explored this idea of putting telescopes in space. And this would help us in getting higher spatial frequency information. Depending on where you put the telescopes, you kind of probe different information. So it's a big question of like, if you put one in space, what actually, or what configuration would you want to use? Because you would get different kinds of science out of them. The challenge is the Event Horizon Telescope has actually been a very cheap experiment as far as science projects go, because of the fact that we've basically used other telescopes and just installed specialized equipment into them. And so like, it's not very clear what the exact cost is, but usually it's quoted under $100 million that the experiment costs, which is pretty cheap, especially compared to like LIGO, which was like $1 billion, right? But putting a single telescope in space at for this wavelength, people at JPL estimated to be about $500 million to $1 billion for a single dish. And so it's a big increase in the money. And so I'm not saying it's not worth it. Definitely we're trying to show that it is, but it's a question of like, what is the best configuration and everything. So there are there are different things that we've considered. One is having a telescope in a low Earth orbit, and that would allow the telescope to orbit around the Earth really, really quickly on the time scale of like an hour-and-a-half period. And what that does, I'm sorry, I don't have the slides here now, but what it does is then it fills up this measurement space very fast. And so you can do things like make movies of black holes much more easily. With just a single dish, you can make a movie. But another thing is if you could go out to space, like, put something closer in an orbit, like that goes out to the moon or so, and that would allow you to get very high, because remember that our spatial frequency that we measure is related to the baseline. So if you have a long baseline, that would give us high spatial frequency information. But the problem is that if we only had a single baseline that's that far out, we wouldn't really be able to make an image very well, because you'd have all this information down here, and then you'd have one point out here, or one kind of set of points out here, and that wouldn't, and so there'd be no way to connect these measurements to these measurements, and so you'd be making up too much information. And so what you could do instead is you could do model fitting. And model fitting would allow you to, like, if you say, oh, okay, I believe it's a crescent model with these only few number of parameters, you could probably do very well, and then get higher information about what's the width of that ring and things like that. You could do very well if you had it point out there, but then you have to believe your model. So it's kind of a trade-off, and it becomes a tug of war between two camps: the people who believe images and the people who want to do model fitting. And there's pros and cons of them. But yeah, that's definitely something that we're pushing for space expansion. But we're wondering, what is the best one? Where do we get the most advantage out of it?
We who are Palomar docents are always channeling George Ellery Hale. And one of the things that he did was in 1928, he wrote an article called On the Possibilities of Large Telescopes. And here you have the chance to have maybe the largest telescope that humanity has ever seen.
Yeah, no, that would be like, oh my God, a telescope the size of the orbit of the moon.
Of the moon.
Yeah, that would be awesome.
Katie, George G had a question in the chat. George, are you still on? Well, let me read the question, if I may. For time synchronization, the VLBI data, what is the source of standard time to which the individual observatories sync their local clocks?
Okay, so I don't know all the details here, but we actually have two clocks. One is more of like a GPS clock that is used, and then we have at each actual site we have a hydrogen maser, which is kind of like clocking the time when we record the signals. So the hydrogen maser has this very precise clocking that we use, and then from that we also record the GPS timestamps. And then from that, we know roughly the baseline between the telescopes. And so we can figure out roughly what the correlation is. And so that's done, that's this initial, this slide. So this is this initial correlation stage here that is using basically that GPS signal with our expected baseline to come out with the correlator output. But now we have to get to sub-picosecond correlation. We have to be accurate to the time of sub-picoseconds, and so our GPS is not accurate and stuff like this. So that's why we go through this extra calibration phase, where actually we chunk up the data and we basically computationally solve for what the time shift is to find where do we get the maximum correlation. And so it's actually done so we have 2 clocks on each site, but then we also have, we actually have to still use computation to do the alignment stuff, to get it into the precision that we need. Did that answer the question?
To the
I'm not-
extent I understood the question, yes. I would defer to George G on that one, but thank you very much. Other questions? Other questions?
I have a
Anybody else?
question. Oh, I have a question. Thank you so much for the talk, and really exciting to hear about your collaborations with JPL about optimal placement of more telescopes in space. But I keep thinking, how are we going to reduce our Earth-based biases in that? And I was so interested hearing about your collaborations with breaking people up into teams and breaking the images, but what's going to happen when we do this in space?
Oh, you're saying that, well, you're saying that when we have telescopes in
Yeah.
space, well, the data would still, at least how we're thinking about it, the data would still have to get down to Earth somehow. And so actually that's one big challenge of it, is the optical communications and stuff, and how you would actually do that. But are you asking about once it's already, the data is here, once we have different kinds of data, how, maybe you can ask the question again, maybe I didn't understand.
Yeah, no, I'm just curious about how that's going to shift, like how you're collecting data and seeing data, because we're so used to doing it on Earth, like the Earth is a camera, but once we go further into space, you know, how is that going to affect the data that you collect? Sure, it's going to be coming back to Earth, but thinking in terms of bias and how we reconstruct images.
Yeah, it's a good question. So, I mean, you know, obviously we can't do this thing where we, where every time we collect data that we spend 2 years analyzing it. And so I think that, you know, when we go to space, we're hoping that, that we're hoping that like eventually this stuff can be more like, as we continue to push the technology and advancing the technology, that we're also pushing the algorithm so that all this becomes even more automated. So the reason it took so many months is because we had to have humans in there and developing new things and everything. But one thing I'm really kind of excited about is using machine learning and artificial intelligence to help us be better scientists and figure out when is the best time to observe, or when is, you know, how do we design new methods? How do we design new, you know, how do we do these things? And so the humans are not injecting themselves as much into the process. So it's a really good question. I don't have a good answer for it right now, but I just think that like, as we start to become, we can build smarter and smarter systems that kind of take some of this power away from us. And in doing so, I mean, we have to make sure that they don't go off, because algorithms also have huge amounts of bias in them too. So we have to design them smartly so that they, that although they have bias, we can never get away from bias, but that we understand our bias. And I think that, yeah, as we just do more of that, I'm hoping that our algorithms will advance in the same way, and so that this stuff becomes more automated and things like uncertainty quantification come out more. So one thing that my group has also been working on that I didn't get a chance to talk about is using machine learning also for uncertainty quantification. So here we ran these grueling parameter surveys that took many months and stuff, where we tried different parameters out and we saw how that affected the images, and it took months and months and tons of computing power. But one thing that one of my group members has been working on is developing a method that you just input a data set and outputs all the possible images, a whole distribution of images. And so that's taking, again, that's mathematically saying like, and where it's mathematically rigorous. This is the uncertainty in our image. And so we don't have to go through all these teams and things like that, which I think was excellent that we did it the first time. But, you know, we can't always be doing this for every new data set. And tools like that allow us to really see our uncertainty and without, see our uncertainty in a more automated way as we, sorry, I don't know the answer other than that, but yeah.
No, that was great. I work for the Center for Responsible Machine Learning at UCSB, and just been really curious about astronomy and machine learning, because that actually seems like going to be a huge part of us in the next 10 years. So
oh, cool.
Yeah.
Well, it'd be great. I'd be fun to talk to you offline sometime and also show you some of the work that we're doing in that as well.
Wonderful. Thank you.
Are there?
Katie, I have a question.
Yeah.
I think you touched on it a little bit earlier, but I didn't quite understand. What if we could view M87 from an entirely different angle, would we see a similar picture, like looking down into a hole, like looking down into an empty bucket? Or would
Yeah.
the picture change entirely?
Excellent. Yeah, great question. So let me go back to that video where I at the beginning. Okay, so what we are seeing, so we have these photons, so we have an accretion disk around the black hole, and it's causing, and it's heated, as I said, to hundreds of billions of degrees. And so the light, you have these light photons kind of flying around, as I said, and it doesn't matter kind of the direction. Like if you just look at this picture, it doesn't really matter where, if the photons are coming from behind or on the side, they're all kind of being bent around the black hole. And so that you kind of, no matter the direction, let me see this again, no matter the direction that you observe the black hole from, you're always going to get a ring of light because the stuff from behind it kind of gets bent around to a ring. But the details of the features of that ring actually are going to change. So, okay, let's say we have a black hole here. Okay, well, I'll play the video just so you can see again. So you can see no matter kind of the direction the light is coming from, it's always going to be bent around the black hole and you're going to get that ring. Now, let's think about what might change when you look at it from different angles. Well, fundamentally, you're always going to get a ring because it's always going to be bending the light from behind it. But let's say we have a black hole here, and then we have an accretion disk moving around it. So when the light from the accretion disk is behind the black hole, it gets bent around and you get that ring shape, just as I showed here. But there is this effect called Doppler boosting, such that because the light is moving so close to the speed of light, when it's coming towards you, it gets brighter, it's Doppler boosted. And then when it's moving away from you, it gets weaker, it gets dimmer. And so what that means is that, okay, you're gonna still always see that ring of light, but when the gas is coming towards you on this side, it's brighter, and then when it's going away from you, it's dimmer, and so you get a crescent. So it's not a perfectly uniform ring. It's going to be brighter on the side that the gas is coming towards you. And so that's why oftentimes it shows like this more crescent T shape. Now the black hole in M87, the jets are coming at us at a 17-degree angle. And so we expect that the accretion disk, so here, like I'm pretending this is the jets, and then this is the accretion disk. So you have a black hole, and your accretion disk is like this. So that means if it was perfectly flat on, it would just look like uniform, but because it's at on the side, coming like a little bit at an angle, that means that the gas, when it's coming towards us, it's gonna be brighter, right? So let's say the gas is moving this direction, it's spinning away from us. That means the gas, when it's on the bottom, is moving towards us, and when it's on the top, it's moving away from us. And what that causes is that asymmetry that we see in the ring. Let me go down to the ring picture. No, where is it? So you can see in the ring that the bottom is brighter. The bottom is brighter than the top. And that we think is because of the fact that the gas on the bottom is moving towards us and the gas on the top is moving away from us. And so there's the asymmetry. If we were to see it at a more extreme angle, the crescent would become even more extreme and the asymmetry would be even more extreme. We're kind of lucky that we see it where we see the full ring still, because if we just saw the crescent, it might be, if we only saw one side bright, it might be hard to show that it was a ring. So we kind of got lucky that it's only partially at an angle. Did that help explain? Did that explain it?
That helps a lot, and to understand a little bit more about why we're seeing the brighter areas and the dimmer areas around the circle, the gas moving toward us and away from us.
Yeah.
Thank you.
Yeah.
Other questions? It is getting late. Excuse me. We probably need to start winding the meeting down. Is there another question right now? Can we take one more? Well, then, if I may, Dr. Bouman, let me finish this off with one kind of general, almost cultural kind of question. When this image was published, we were then doing tours of the Hale telescope for the public for scout groups, for high school classes, biker gangs, and others. And it seemed as though everyone, the kids all had seen this image and at least had some idea of what it was all about. You have been talking about this to the public for a while now. Have you considered the question of why this image has evoked a degree of response, a degree of cultural resonance?
Yeah, it's a great question. And I'll first start off by saying that when we published the image, released it to the public, we were not at all expecting the reception that we had. It was, at least to me, a complete surprise. I mean, I thought, okay, the science community would be excited, but I had no idea that it would resonate with the public like it has, and it took us all by surprise and by storm, and it's great. I mean, it's awesome, and it's so amazing to see like young kids being excited about it. Like I remember a couple days after the announcement, or like a week after the announcement, there was this young girl who came to me, and she was with her dad, and she was telling me, she wasn't asking me about black holes, she was telling me all about black holes, and it was so amazing. And then I remember like asking her, oh, what do you want to do when you grow up, thinking she'd want to be like a scientist or an astronaut or something, and she said, oh, I want to grow up to be Elsa, the princess from a Disney movie. And I thought it was, I thought it was amazing, because I was like, this is a normal, regular little girl who's so excited about science. And so why, I don't know, like why I thought about it. I thought, why, I'm not an astronomer myself, actually. I come from the computer science and artificial intelligence kind of community. And so, what drew me to this, I think, is drawing a lot of other people, this idea of like imaging the invisible, like doing this thing that it feels like it should be impossible in so many different ways. Well, first, it's impossible. How do you see a black hole that doesn't emit light? That's like the first impossibility. Then how do you image this thing that is the size of a grain of sand from across the country? It's another like impossible thing. How do we build an Earth-sized telescope? So there are all these kind of like impossible things, I think, that, that by bringing people together, we were able to accomplish them. And so I think that, I don't know, I think it's a form, like, it's kind of, even to me, like thinking about it, it's like somewhat inspiring. Like, okay, if you put people together, you bring together a great team of people and you put your minds together, you can do things that at first glance seem impossible. And so, I don't know, that's what I think it makes a lot of people really, I don't know, excited about it. But I'm really glad, and I'm glad that it has, hopefully inspired a new kind of generation of scientists and engineers, hopefully.
Well, wonderful approach, wonderful answer. Thank you very much. Dr. Katie Bouman, that was a wonderful presentation, and thank you for joining us.
Yeah, thanks for inviting me and for all the good questions. It's great.
And to bring the meeting or to close, let me briefly talk about the next speaker in the Greenway series. In 2 weeks, on June 19th, excuse me, Zoltan LeVay will give a talk titled Creating the Pillars: How Science, Content, and Emotional Impact were joined in the images from the Hubble Space Telescope. Until his retirement in 2018, Zoltan LeVay was a principal science visual developer at the Space Telescope Institute. During his 35-year association with STSCI, Zoltan built the team of imaging specialists and communications experts that produced the long succession of spectacular Hubble telescope images that are now so much a feature in our popular culture. Join us in 2 weeks and meet the creator of the pillars of creation. So thank you again to Dr. Bouman, and my thanks to all of you, to everyone, for attending and supporting the Greenway Talks. I really appreciate you seeing you here. And with that, I'll close the meeting and we'll see you again on June 19th. Thank you very much. Bye-bye.
Thank you, Steve.
Bye-bye.
Thank you, Katie.
Bye-bye.